Okay, hello everyone. In this very video, we are going to continue from where we stopped in the last video. We'll be doing further examples on the principle of mathematical induction. So here we are asked to establish the identity by induction that 1 over 1 dot 2. That 1 dot 2 actually means 1 times 2, okay? Plus 1 over 2 times 3 plus dot 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 plus 1 over n plus 1 equal to n over n plus 1. Already we've established the fact that the left hand side is equal to the right hand side. Okay, so to continue, we start by saying let Pn be the statement that will repeat the same thing. 1 over 1 times 2 plus 1 over 2 times 3 plus dot dot plus 1 over n plus 1 equal to n over n plus 1. Okay, so we start with the basis step. Remember, the basis step means that the first step is that to show that the statement is true for n equal to 1. The left hand side, you can see that your left hand side is half. Is already clear because when you say 1 over 1 times 2, it simply means 1 over 2. Okay, so the left hand side is half. Now, as we continue, the right hand side, when we pick the right hand side, which is n over n plus 1, and you substitute 1 for n, you are going to get 1 over 2. Okay, exactly what we see. So you can see that the left hand side is equal to the right hand side. We can now say that the statement is true for n equal to 1. That is it. That's the first thing we want to talk about. Now we move to the inductive step, which means for n equal to k. If we continue, we are going to assume here that the pk is true and proceed to prove that pk plus 1 is true. So by the inductive hypothesis. Now we continue. So you see, I have the same statement, but just that n has now been replaced with k. Whenever I see n, I have k. Now that leads us to, for n equal to k plus 1, remember what we want to establish, that when I substitute n equal to k plus 1 into this Pn, I will get exactly the same value, and we have this. So if you notice here, there is a substituting here in this value. We have k into k plus 1. And if you see, wherever you see k, you substitute k plus 1. So that's what we have here. Let me quickly do that for us here. Remember, we have 1 over k plus 1. Now, if I'm repeating this now with, I'm going to have 1 over k plus 1 in place of k, okay? Then in place of this k, I'll also have another k plus 1, then plus 1, which makes it k plus 2. That's why we have what we have here. Sorry, it's being covered by the cursor. Okay, and remember we said that whatever we add to the left-hand side, we also add to the right-hand side. So we already have it added here at the right-hand side. Of course, the next thing is to solve the right-hand side. So we solve the right-hand side. We see that in the next. We see that here. So that is it. You can see what I have. This is where the case statement stopped. Sorry, excuse me. This is where the case statement stopped. And when we substituted k for k plus 1, this is what we got. So this that we've now added to the left-hand side, we have to add it to the right-hand side, and we have this. Okay, so if we are to continue from there to continue solving the right-hand side, if you find the LCM is k plus 1, k plus 2, which k plus 1 in k plus 1, we cancel k plus 1 to remain k plus 2. K plus 2 times k, we have k plus 2, then finally plus 1. Okay, that's finding the LCM. If we expand the numerator, k times k is k squared, k times 2 is 2k, then plus 1, which when you factorize, you're going to get k plus 1, k plus 1. You can see that certain things can cancel out. K plus 1 here can cancel k plus 1. So I'm left with k plus 1 over k plus 2. Okay, which is the same as when we substitute n equal to k plus 1 into Pn. So you can see this is my Pn. If I replace n with k plus 1, I will get this, which is exactly the same value we got here from the hypothesis. With this, we can say that the statement is true for all positive integers. Okay, so that is that. We are going to see one more example here. We're asked to establish by the identity by induction. That's the a plus ar squared plus dot 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 plus ar n minus 1 is equal to a into r minus r raised to power n minus 1 all over r minus 1. Okay, we start by saying let Pn be the statement. We make that statement again. And like we always do, we start with the basic step. Basic step is n equal to 1. Now, and the left hand side, you can see that your a for n equal to 1, the first term for the left hand side is a. Okay, now let's see for the right hand side. Your right hand side, you have a into r raised to power n minus 1 all over r minus 1. If you substitute r to n to be 1, you are going to have a into r minus 1 over r minus 1. Okay, which r minus 1 can now cancel r minus 1, and we are left with just a. So you can see that we have a in the left hand side, we have a in the right hand side. We can conclude that the statement is true for n equal to 1, because the value we have on the left hand side is the same value we have for the first term, n equal to 1, on the right hand side. Now we go with the inductive step, which means replacing all the n's with k, and just like we have here, assume that the pk is true and proceed to prove for pk plus 1. We have this. So a plus ar squared plus dot 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 plus ar k minus 1 is equal to a into r raised to power k minus 1 all over r minus 1. Okay, just replacing n with k. Then we continue for n equal to k plus 1, which, for n equal to k plus 1, we must find the k plus 1th term, which is the next term after k. That means substituting k for k plus 1, and we are going to have this. I know that's not very clear, but if you have the ark minus 1, this is the kth term. This is the first term, second term, third term. Okay, then this is the kth term. If you put k to be k plus 1, we are going to have ar. This k is now k plus 1. Then you have minus 1. So 1 minus 1 is already 0. So you have just ark, which is exactly what we have here on the left hand side. And since we've added it to the left hand side, we should also add it to the right hand side, which is exactly what we've done. Okay, so which is this ark here on the right hand side. Now if we move on, that's what we have in the right hand side. A into r raised to power k minus 1 all over r minus 1, then plus ark. Okay, find the LCM. R minus 1 is the LCM. That shouldn't surprise you. That's what we have. When you make r minus 1 is the LCM, so you're going to have ark into r minus 1. And open the bracket. When you open the bracket, you get ark minus a plus ark plus 1 minus ark. You're going to wonder, how is that? When we say ark times r, r means r raised to power 1. So by indices, you're going to have ark plus 1. That's how we got that, by indices. Okay, so you notice that from what we see here, ark here cancels ark. Ark cancels ark, minus ark is 0. So we are left with ark plus 1 minus a all over r minus 1. We can factorize a to give us r raised to power k plus 1 minus 1. Okay, so from here you can see that it is the same as when we substitute. It is the same as when we substitute n equal to k plus 1 into Pn. So the left hand side there is Pn, which is a r raised to power n minus 1. If you substitute k plus 1 for n, you get rk plus 1 minus 1, which is exactly the same thing as what we obtained here. And once we can achieve this, we can now say that the statement is true for all positive integers. Okay, watch out for the third video for the next lessons. Thank you.